We're back. This time we are going to talk about carbon X bonds. And we're going to start our discussion by looking at the CH3X fragments. In other words, we're going to look at methyl molecules. And this could be a methyl halide, or it could be an alcohol. It could even just be methane. And we're going to compare all of these bond dissociation enthalpies and try to rationalize what's going on. Once again, bond dissociation enthalpy entails that we're going to uh, homolytically cleave the covalent bond. So we're going to produce radicals. So first things first, you will notice, much like in the HX example in the previous video, the carbon-fluorine bond is still the strongest in the series. Not as strong perhaps as the HF bond, but it is kind of strong nonetheless. And both what happened in the HX example and the methyl X example here, this is due to the greater electronegativity difference between carbon and, in this case, fluorine, right? That gives you the greatest difference in electronegativity, so you have a stronger bond overall. Now compare that to the carbon-hydrogen bond. The electronegativity difference is very small. Basically, it's a nonpolar bond, so you don't get much of a charge separation, but what you do get is a shorter bond. And because the carbon H bond is shorter, that alone makes this a semi-strong bond, right? And so these two are kind of in line with each other. And as a matter of fact, carbon-fluorine bonds are so strong and difficult to break that there are many molecules like Teflon that contain carbon-fluorine bonds that for all intents and purposes are inert to most chemicals. It doesn't matter if the chemical is a strong base, a strong acid, a corrosive substance, a redox active substance. Those chlorine-fluorine bonds tend to be pretty strong and difficult to break. So Teflon becomes a rather inert substance that you can use to either store your chemicals or run your reactions in. So something to point out. And the carbon-hydrogen bond is also relatively strong. So those are also difficult to break. And in essence, being able to break carbon-hydrogen bonds is part of the holy grail of synthesis, because being able to break those bonds so that you can synthesize bigger or more complex molecules will be phenomenal. In essence, this is almost like the bottleneck effect of synthesis, but there are a lot of examples in catalysis that allow you to do to some extent just that. Okay, now moving on the series, we see that the carbon-oxygen bond for an alcohol and the carbon-carbon bonds are roughly in the same vicinity, so they're the ones probably second tier in terms of the strength. And the reason why is because for the carbon-oxygen bond, you still have a large electronegativity difference, not as large as the carbon-fluorine bond, but it is still large. So you fall a little bit below the first two values as a result of the smaller difference in electronegativities. The carbon-carbon bond, on the other hand, the electronegativity difference is literally zero between carbon and carbon, but you do have a still relatively small bond, and that's also true for the carbon-oxygen bond. So you have relatively, intermediate values for this bond dissociation enthalpies. And then when you look at the carbon-halogen bonds, so the carbon-chlorine, the carbon-bromine, the carbon-iodine bond, as the size of the halogen increases, you see a decrease in the bond dissociation enthalpy. And that is definitely true for all of the halogens. The carbon-fluorine bond is the strongest, the carbon-iodine bond is the weakest. All right, so we see that relatively clearly just by looking at electronegativity and size of element. So now let's take a look at a similar picture, but instead of focusing on the methyl component, let's make this a little bit more of a variety. Let's make it a little bit more diverse. So here what you can see is that the values for X, they're still fluorine, hydrogen, etc., for methyl in the first column. But then I've also introduced an ethyl group, an isopropyl group, and a tert-butyl group to represent the second, third, and fourth columns. And one thing that I also want to point out, we're going to be using this terminology more as the semester goes on. But whereas I refer to CH3 just as methyl, and you could still refer to CH3, CH2 as ethyl, the fact is that the CH2, where the X is going to be bound to, already has a CH3 bound to it, or better yet, the CH2 unit has a connection to another carbon. We call this a primary carbon. So the X will be bound to a primary carbon. And over here, the CH, which is going to be where the X binds to, already has connections to two other carbons. So this is a secondary carbon. And finally, for the tert-butyl case, the central carbon over here where the X is going to bind to, this carbon already has connectivity to three other carbons. So this is what we call a tertiary carbon. So you'll hear me refer to them as primary, secondary, and tertiary, and of course methyl, right? Okay, so the one thing I want to show you is that generally speaking, the trend seems to follow in the same overall direction. We see that the carbon-fluorine bond is the strongest among all of the series. We also see that the carbon-iodine bond is the weakest in every single one of the series. We see that the carbon-carbon bond is intermediate. We see that the other halogens are also a little bit stronger as the size of the halogen becomes smaller. So we kind of see a general trend that we observe for the methyl group. But the one thing you will notice is that when X happens to be OH, something interesting takes place, right? Notice that going from left to right, the bond dissociation enthalpy increases, relatively speaking. However, for every other group, going from methyl to the tertiary carbon, the value of the bond dissociation enthalpy is actually decreasing for fluorine, decreasing for hydrogen, decreasing for carbon, decreasing for chlorine, decreasing for bromine and iodine. So actually, the carbon OH functionality is in essence a bit of an outlier. And we're going to get back to that in a second. But the one I want to highlight is that for most of these substitutions for X, what we are seeing is that the bond dissociation enthalpy is larger for methyl than a primary carbon, then a secondary carbon, then a tertiary carbon. In essence, the smaller one for, in this case, 1, 2, 3, 4, 5, 6 out of 7 cases, the tertiary tertiary CX, leads to the weaker and the lower bond dissociation enthalpies. So let's examine this a little bit more clearly. Why would that be? Why would increasing the substitution of carbon onto the central carbon atom lead to changes in the bond dissociation enthalpy? Well, this has to do with the transition state, and in this case, the intermediate that you are producing in the course of forming that radical. So what I want you to notice is that all three of these molecules, so we have methyl radical up here in red, then we have the primary radical in orange, the secondary radical in green, and the tertiary radical in blue. In each one of those cases, notice that the shape is on purpose depicted as trigonal planar. And that's because the lone electron, the unpaired electron of this radical, lies on an empty orbital that is unhybridized. So you got that trigonal planar shape, and this is going to be crucial to explaining what's happening. Now, if you think in terms of energy, going from the starting material up until this intermediate, if it takes more energy to break the bond, one rationalization for this outcome is that you're producing an intermediate that is a lot higher in energy, that is more unstable. And so what I would say is that the tertiary radical is going to be more stable than the methyl radical, right? And in fact, those are the extremes. So why would that be, right? So here's the clearer picture. So this is the bond association enthalpy, right? This is the lowest one for the tertiary, a little bit larger for secondary, a little bit larger for primary, and a lot larger for the methyl. So what is happening here? Why are we seeing this increase in radical stability as you increase the substitution of of the central carbon with other carbon-carbon bonds. Like what is about that substitution that allows the stabilization? Well, in the methyl radical with that trigonal planar shape, all you have is carbon-hydrogen bonds, right? And the hydrogens are cylindrically symmetrical, but that's pretty much it. They are incongruent. They don't line up with a p orbital, so you cannot really mix that s orbital of the hydrogens with the p orbital to do anything molecularly speaking. So there is no actual orbital overlap that could help stabilize this molecule. This is basically out of luck. But when you start looking at the primary substitution versus the secondary substitution versus the tertiary substitution, what happens is that now that you have that carbon-carbon bond, the carbon on the end has other bonds present. Specifically in this case, we're talking about carbon-hydrogen bonds. And if we draw them out in their typical tetrahedral shape, what you can see right now is that you have a carbon-hydrogen bond that at any given point in time is going to be present parallel to this empty, well, or semi-occupied p orbital. In fact, we're calling this orbital the SOMO, which stands for singly occupied molecular orbital. So you have this carbon-hydrogen bond that lines up parallel at some point in time as the bond rotates with the p orbital that has that empty electron. And as you go from primary to secondary to tertiary, you actually have more of those outcomes present. Now you might say, well, this kind of looks bad because you got electron in the middle that's now being lined up with electrons next door. That seems like an electron-electron repulsion type of situation. And you'll be right about that. There is some of that in there. But in addition to that, you have a stabilization that comes from the fact that this single electron is unpaired. So you have only a spin-up electron, and technically you could put a spin-down electron to pair it up, right? And that's kind of what we're going to utilize right here. So each one of these bonds can help out stabilize that electron that's by itself and give it a somewhat paired up essence, if you will. And the way it basically does it is by pairing up without breaking the covalent bond adjacent to it. It pairs up with the electron that has the opposite spin as itself, right? So if this is spin up, it starts interacting with that spin down electron. And if you have more substitutions present on the carbon, then you're going to have more of those spin up, spin down interactions. This is what we call hyperconjugation. It's a means for the molecule to stabilize itself without actually giving away the electron or relocating the electron. So the more substitution, as you can see here, the better you are at stabilizing that single electron in the middle, right? Just by almost by proxy, if you will. So this is electron-electron stabilization by proxy, hyperconjugation. All right, so that explains why you are dealing ultimately with a more stable tertiary radical, as shown here in blue, compared to a secondary, which itself is more stable than a primary. And of course, the methyl radical does not have adjacent CH3 groups, so it does not have this hyperconjugation event going for it. So it's at the most disadvantage. Okay, so that gives you an idea of how the bond strengths relate to the corresponding carbon X bonds. In the next video, we're gonna diversify the idea for organic molecules a little bit more. We're gonna come back to talk about the ROH bond and see why we saw discrepancy in the original table. So I'll see you in the next video.